Hello and welcome to my poster called Using Network Propagation to Walk Through the Enhancer Gene Regulatory Network. My name is Dennis Hecker and I'm happy that you're interested in this topic. To give you a little bit of background and to tell you what motivated our work, I want to briefly introduce the Generalized Activity by Contact Score, which is a method for predicting enhancer gene interactions. And the basic assumption is that if an enhancer is highly active and it has a high contact frequency with the gene, it's likely to be relevant for the regulation of the gene. So as input, we need a measurement of enhancer activity, which could be DNA-seq, ATAC-seq, or something similar, and also the 3D contacts in the genome. We plug these two into this equation here, so we take the product of the contact with the activity and divide this by the sum of the same product for all other candidate enhancers in a defined window. Additionally, we summarize this across all annotated transcription start sites of a gene, so not only, for example, for the 5'. This is all part of a pipeline called STAIR. If you want to know more details, just check it out, visit our website, or get in contact with me. What we found is that this score works pretty well for predicting enhancer gene interactions, and it's also convenient because it only requires one measurement of enhancer activity, because the contact part you can actually replace, for example, by an average IC matrix or by a contact estimate, which is calculated based on distance. But there are also a few downsides. So each gene is treated independently, so you can't really compare across different genes. You don't know which might be more regulated or less regulated, which is more complex. And also that we don't get any information about enhancer-enhancer interactions or potential gene-to-gene interactions. And we thought we could actually include this if we model enhancers and genes together in a joint network. You can see such a network here, where we draw the nodes of the enhancers as circles and the nodes of the genes as squares. The node values are the enhancer activity, so we have values for the enhancers, but the genes still have an activity of 0. We draw edges between the nodes that also have a contact in 3D, so for example from an IC matrix, and we also quantify the edge values with the respective contact, which also allows us to include gene-to-gene contacts as well as enhancer-to-enhancer contacts. Now, we want to apply network propagation, more specifically random walk with restart. And what we need for this is a transition matrix, which tells us how likely it is that if we are at one node, we transition to another node. And to fill this, we can use the contacts that we get from, for example, an IC matrix. And now to propagate our node values throughout this network, we take the transition matrix and multiply it by this vector of node values. And this is the random walk with restart because you always add a certain percentage of the starting values of your node. So for example, if you chose a restart probability of 0.2, you will always give 20% of your starting values back into the network. So we wanted to see, does this actually work if we use this setup to predict enhancer gene interactions? And we did so by iteratively removing enhancer nodes to score each enhancer to gene link. So on top you see the steady state unperturbed propagation. We have a smaller example, 1 gene and 3 enhancers, and we see this one here is more active. We have our node values at the starting point, and then we propagate the enhancer activity through this network iteratively until we reach a certain point where there is not much change happening anymore, and we get a final node value vector here, P68. And then we do this again, but when removing one enhancer. So in this case, we take out enhancer 1. We call it P hat now, or vector of node values. We do the propagation again, and we end up with a different node value vector, which we call P hat here. And now to get a score for each gene to each enhancer, we take the difference of the node value that we get at gene 1 in the steady state, subtracted by the perturbed version of this propagation. And this score we call a delta. To see how well this works, we tested this on 3 different CRISPR-I perturbation screens, so experimentally validated enhancer gene interactions. And in yellow, you see here in the precision recall curves the GABC score, so this was what we wanted to compare to. And the delta here is the score that we get from the network propagation. And as you see, it actually works not as good as the GABC does. It gets into the same direction, it's not really that bad, but it doesn't reach the accuracy of the GABC. So What we also did is we tried a lot of different things, changing the setup of the networks to see how does this impact the prediction accuracy for the enhancer gene links. And what we found is that you take the delta score relative to all other enhancers per gene, it works pretty well, it improves the accuracy. Adding pseudocounts, however, on the contacts works pretty bad, because I guess that you just blow up the network and get too many edges. But what we also saw is that we remove the enhancer contacts, it doesn't really change much, which was a little bit disappointing, to be honest. What we also saw is that similar to the GABC, if we consider all transcription start site, it works better than just using the 5' TSS, and also if you use larger windows, it also works better. But I want to point out that there is difference across the different CRISPR-I screens. On some, certain methods work better than on others. Our conclusion was that despite a slightly worse accuracy for these enhancer gene interactions, it has a huge advantage because it gives you a score per gene, and it also allows to incorporate any other information into the graph, which brings me to an application where we want to test how well it works if we propagate SNPs to prioritize disease genes. So first is that we want to find enhancers which are affected by a SNP or which just happen to incorporate or to contain a SNP. And then we build a network from these where we only include enhancers which have a SNP as well as all genes, and also add gene-to-gene edges as protein-protein interactions from the string database. An example, you can see here what you could, for example, do with it, where we show the top 10 genes for a certain set of cell types, where we use the enhancer data from to see how much activity of the enhancers with a SNP is propagated to the different genes. What we still have to do is we need a proper background model to also get a p-value. We need to evaluate the plausibility of the results. This is all very work in progress. And also we want to test different modalities. Thank you very much for your attention and happy to hear comments from you.